Hey everyone. So last time we looked at vector spaces, and vector spaces were a collection of things V, and we could do two things on vector spaces. They had addition, and we had scalar multiplication. And maybe just to remind you, we could look at something like R2, which is columns of numbers A, B, and we could add them in kind of the way you'd expect. So 1, 2, plus 3, 4 is 4, 6. And we could scale them also as you'd expect. So 5 times 3, 7 is 15, 35. This time, we're going to introduce a new function called an inner product on our vector space. An inner product eats two vectors. So we will say eats two vectors and gives us back some number in a field F. So just to remind you, if you're not sure about what field, this for us is just going to be the real numbers or the complex numbers. And we're going to write it like this, where V and W are going to be our two vectors, and this is going to be some number. Now, an inner product has to obey certain rules. Firstly, it has to be linear in the second argument. So what I mean by this, if I put some addition and scalar multiplication inside here, then this must be the same as VW plus BVZ. So if there's numbers, I can pull them out the front. It splits over addition. And this property is called linearity. We must have another property, which is called conjugate symmetry, which says VW is the complex conjugate of WV. So conjugate symmetry. Then we should also have that something in a product with itself is always greater than or equal to 0. The reason we want this is we're going to use inner products to actually allow us to talk about the size of vectors, and we don't want negative sizes. And the final product, or final important thing, is we should have V inner product with V equal to 0 implies V is 0. So really what this means is the only thing which has size 0 is a 0 vector. So these are the 4 properties we need for us to have an inner product. Now this sounds probably horribly abstract, so let's try and look at an example. And one example is one you might have seen before, called the dot product. And the dot product, and we'll look at, let's say, R3. The dot product on R3 is defined to be, I take 2 vectors in R3, so that's just 3 column of 3 real numbers, and we define a dot product on them to be AD plus BE plus CF. So really, it's just the first two numbers multiplied together, plus the second two numbers multiplied together, plus the third two numbers multiplied together. And this is an inner product. We can check all the properties. So let's maybe check a quick one. Let's check that something dotted with itself is always positive. So if I do ABC dotted with ABC, I get A squared plus B squared plus C squared. And since a square of a real number is always positive, this whole thing is always positive. And you can check the rest yourself as a good exercise. So the reason we care about this is inner products allow us to define a couple of things. They allow us to define the size of a vector. And we define the size of a vector by writing this. The size of a vector is just the square root of its inner producted with itself. Now, to see why this seems like it's a sensible definition, let's look at the dot product on R2. So once again, we'll use the inner product we've talked about before, but this time we'll just restrict it to being columns of two numbers. So we'll get AC plus BD. And the size of a vector, so we'll say the size of AB is the dot product of AB with itself, square rooted, which is the square root of A squared plus B squared. And this you should think of as just being exactly like Pythagoras' theorem. We have some arrow which goes A this way, B this way, and the length of it is just A squared plus B squared, all square rooted, which is exactly where this definition of the size of a vector comes from. Now, we can do another thing with this, is that we can actually use an inner product to define the angle between two vectors. So the angle between two vectors is defined in the following way: that the cosine of the angle between two vectors is the inner product between the two vectors divided by size of A and the size of B. Now, the reason we like this or maybe we should just see an example, which is right. If we, or maybe let me draw the picture, that might be the most helpful thing, which is if I have some vector A, vector B, there's an angle between them, and the cosine of this angle is defined by this. Now, let's look at one final example, which is inner products for complex numbers. So let's look at C2, which is, once again, columns of two numbers, but this time we allow A and B to be complex numbers. And the important thing is that we can't use the definition we had before, because before we had this. But now if we swap them, this will give us the same thing. However, really, we wanted this to be the complex conjugate of this. So something must be going on. So what we're going to do is instead define it to be a complex conjugate C plus B times the complex conjugate of D. So in this side, because C is first, we'll get the A complex conjugate and the B complex conjugate. So this works out as we wanted. So this probably seems very weird and very abstract and not maybe the most useful thing. It's going to turn out to be really important in quantum mechanics. So thank you all for listening, and I hope to see you again